Hey there everybody, and welcome to a video on section 9.3. This is the last section before we reach our last big application of the course. In sections 9.4 and 9.5 we study ecological models. This section 9.3 is the last piece we need to fall into place before we study those models. So the point of this section is to provide a bridge from section 9.1, and recall section 9.1 only cared about linear systems, and we built a lot of language around slope fields of those. So a bridge from that to sections 9.4 and 9.5, the systems in those sections are non-linear. These ecological models we will study are non-linear. However, they are what is known as locally linear. So section 9.3 is about local linearity. What does that mean and how does it work? And it's a tremendously beautiful idea. This section is very nice. So just to get you thinking about this term, locally linear, to motivate that using things that you already know, here is a graph of the function x squared plus 1. This, of course, is not a linear function. This graph is not a line. However, if you pick your favorite point, like 1, 2, and then you draw a tangent line through that point, like so, right? And then you zoom in on that point, like a lot, like that. Suddenly there, right? Let me take the tangent line off. Suddenly there, this x squared plus 1 function looks a lot like a line, doesn't it? Right? And the red and the black are almost on top of each other, right? The tangent line and the original curve almost on top of each other. And if you zoom in enough, right, eventually you can't tell a difference between the red and the black. So if you zoom in enough, the tangent line and the curve itself are indistinguishable. That's what it means to be locally linear. At any point, the tangent line, it turns out, is an approximation of the curve. This is true for any smooth curve. Any curve whose derivative exists, and therefore a tangent line exists, is locally linear in this sense. So on the one hand, this is a fairly simple idea, right? Like, well, of course, if you have something, a curve like x squared plus 1, and you zoom in on it enough, of course you'll see something linear. So on the one hand, it's a simple idea, but on the other hand, it's a profoundly deep idea. So much of calculus runs off of this idea. This is why we care about tangent lines in the first place, right? Think about all the times in your calculus careers where tangent lines come up. And perhaps you wondered why. Why do people care about these geometric objects so much? It's because of this, because tangent lines can approximate a curve very well at the local level if you zoom in enough. And so many things run off of that. And one big thing that runs off of that is Euler's method. That method was just stitching together tangent lines to approximate a smooth curve for you. So we couldn't have solved those SIR models without this fact, right? That smooth curves are locally linear. So it turns out that same kind of idea occurs here, but with linear systems of DEs, or nonlinear systems of DEs, not nonlinear functions like x squared plus 1. And it's a super nice idea. Okay, so here's some motivation. So let's let x of t and y of t represent populations of two different species. We'll measure them in thousands so we can keep the numbers nice. Suppose that these two differential equations model the growth of those two species over time. Notice these systems are not linear. Why is that? Because you have like an x squared term up here, you have an xy term, y squared term, xy term. Right? All those terms mean the system is not linear. You cannot model this system with a matrix like we did back in chapter 7. Okay, so let's find the equilibria and critical points of this system. So as always, to find equilibria, the derivatives are 0, so you can have Wolfram solve the system for you. And when you do that, Wolfram spits out these 4 points. So here are 4 equilibria in the system. Everything is measured in thousands here. So this is like 500, 500. So this equilibrium is a coexistence equilibrium for the two species, where they each have 500 individuals. This equilibrium here means that the first species, species X, has died out, and the second species has 750 individuals, and so on. There's a mutual extinction equilibrium. This equilibrium here, species X has 1,000 individuals, and species Y has died out. Which of these equilibria are stable, which are unstable? In particular, suppose I ask you like this concrete question. Suppose population X starts like that, population Y starts with 900. What happens in this system? Do they both die out? Does one dominate the other? Can they coexist? Etc., right? These are the questions we'll care about in 9.4 and 9.5 exclusively, right? That's what those sections are about. In this section, I'll just show you how you can get an idea of how to answer questions like this. How do you analyze this nonlinear system with the language from section 9.1? So here's the main result of 9.3. Here's the punchline. Suppose you have a nonlinear system like this. X prime equals some stuff with x and y's in it. I'm going to call that stuff F. Y prime equals some stuff with x and y in it. I'm going to call that G. Suppose you have an equilibrium, x naught, y naught. Then the nonlinear system, so this dude here, near this point, so if you zoom in on this point, okay, what you will see is this linear system as if it were at the origin. So let me just say that one more time. If you have a nonlinear system like this, so again, like this, right? This is like capital F, this is capital G, nonlinear functions, and you have some equilibrium, like say the origin, or 0.5, 0.5, or whatever. There are 4 of them from the slide, right? If you zoom in on that equilibrium, what you will see is a picture like what you saw in 9.1. This is a linear system here, where this is centered at the origin. So it's hard to communicate up front how nice this is. I want to show you this illustrated in a second, but this is a very nice result. This matrix here with these partial derivatives, f partial x, f partial y, and so on, that's called the Jacobian of the nonlinear system. And this result is saying that if you want to measure how the nonlinear system is behaving near this point, what you can do is you look at this linear system here. And looking at this linear system means going back to section 9.1, where the matrix is the Jacobian evaluated at the equilibrium you care about. So let me show you how this plays out and then show you a visual so you can really see what's happening. So here's the example I started with. X prime equals x, 1 minus x minus y. I've expanded that so that it's easier to take partials. And y prime is this stuff here. Again, expanded, easier to take partials. How does that system behave near this equilibrium? There were 4 equilibria. Let me just pick one, 0.5, 0.5. Well, this previous slide says you build this matrix and then plug in the x naught and y naught values. In this case, x naught and y naught are both 0.5. So let me build that matrix. So the Jacobian is the x prime stuff. Here's the x prime stuff partial with respect to x. Here's the x prime stuff partial with respect to y. Okay, so x prime stuff partial with respect to x is this. You treat y like a constant, right? So you get 1 minus 2x minus y. If you take that same stuff and treat x like a constant and differentiate, you get negative x. So again, these are just like friendly Calc 3 partial derivatives, you know. Here's g. If you take its x partial, you should get negative half y, which is here, and so on. Here's the y partial. So once you have this matrix, notice there are x's and y's all over the place. So you can plug in a half for x and a half for y, and you will get this linear system here. So how does this nonlinear system behave around this point? The answer is it looks just like this picture from section 9.1, but at the origin. So basically this half-half guy is playing the role of the origin in that system there. So this linear system, we know how to analyze. We just get eigenvalues, and we use the eigenvalues to characterize things like stability. So that linear system has these eigenvalues. They're both real, distinct, and negative. So you can reference table 9.1.1 to learn that this is an asymptotically stable node. Okay, so let me show you what's happening here. Bring up the visual. Okay. So here's the slope field for that system. These red circles here are the 4 equilibria that the system had. So I'm going to focus in on the 0.5, 0.5 one for a second. Well, I guess first let me just say, if you sort of like scan your eyes across this whole picture, right? Globally, this system looks nothing like any of the pictures from section 9.1. If you go through all the pictures from section 9.1, globally, you're not going to see anything that looks like this. However, if you start to say zoom in on some points, you'll start to see pictures like we saw in section 9.1. So if you think about the 0.5, 0.5, if you sort of focus your eyes just right here, notice what you see is kind of like a node, right? You get sort of this eigenvector line with things flowing to it, okay? So let me just zoom in on that, like this. Okay, so really close to 0.5, 0.5, here's what that system is looking like. So I want you to take a mental picture of this, okay? So keep that in your mind. And now let me zoom out, move over here. I'm going to turn this system off, and then I'm going to plot this linear system here. Okay, so here's a plot of that. Okay, see this? This is the asymptotically stable node type picture from section 9.1. And notice you got an eigenvector line slanted, right? It's going down from left to right like this. So again, did you take a mental picture in your head of the other guy, right? Let me turn this off, turn the original guy back on, and again, zoom in around the point, 0.5, 0.5. See? That's the same picture. Do you see that? Isn't that nice? Isn't it nice that it works like that? So again, if we were in class, I would force you all to show your pleasure at this. Whoop. And admit how nice this is. Okay, there we go. So again, take a mental picture of this, right? Zoom out, turn all this off. Here's the linear system, right? So you see that? So around here, right, the nonlinear system behaves like this. So what does that mean? That means if you have this nonlinear system like this, zoom in a little bit. You have this nonlinear system like this. Globally, this is not a linear system. But if you zoom in enough around your equilibrium, you will see something linear. You'll see a picture like what we saw back in section 9.1. Just like when we zoomed in on x squared plus 1, what did we see? We saw something linear. We saw like a tangent line, right? A literal line. Same thing happens here. You zoom in on your equilibrium, you will see not a line, of course, right? But you will see a linear thing, a linear object, a slope field that came from a linear system. That is just so nice. And I can't emphasize enough how nice that is. What a nice way to sort of end this course, right? To sort of throw back to this parallel of the foundation of Calc 1, right? That if you zoom in enough on something nonlinear, you will see something linear. Okay, so now what I want you to do, oh yeah, these should be your reactions, by the way. First, you should be shocked by this. There's no reason to think this is true. It's so nice that's true. So in class, your jaw should have dropped when I showed you this, okay? Then you should be super happy about that. How nice is that, you know? Like, it's just like a massage for my brain to look at things like that. It's nice how it works. Okay, so now exercise 1, I want you to pause the video and repeat the same analysis. So build the locally linear system and classify it, but for the equilibrium 1, 0. Okay, so assuming you're back, you should have gotten this locally linear system for 1, 0. 2 real eigenvalues of opposite sign gave a saddle point. So 1, 0 in the original system was unstable, and it looked like a saddle. So I suppose it's nice that the extinction of one of the species, that outcome is unstable. I suppose it's nice that coexistence is stable. So let's go back over here, and now let's focus on the point 1, 0, which is over here, okay? So I'm going to zoom in on 1, 0. Okay, so locally you see a picture like this. You see sort of the saddleness is you got sort of a dominant eigenvector line here, and then you got a non-dominant eigenvector actually parallel to the x-axis, just on the x-axis. So you get sort of 4 pieces of the plane, right? Flow up that way, flow up that way, flow down that way, flow down that way. Okay, so take a mental picture of this. Keep that in your mind. And now let me go over to the origin. I'm going to turn this system off, and then I'm going to turn on the system that you got, right? This guy here. And it looks like that. It's the same, you know? It's the same as what we saw when we zoomed in on 1, 0. Isn't that nice? The answer is yes. It is nice. Okay. So now, let me just do one fresh. So this is your second exercise. So again, pause this video, but do the whole thing here. So find all the equilibria of the system, classify them, and like just build the locally linear system and classify them by type. So whether they're a node or a saddle or whatever, and then say their stability type. So pause the video and then come back. Okay, so assuming you did that, the equilibria are -1, 1, and 1, 1. And by the way, I guess I should show you Wolfram doing that. So Wolfram, of course, can do any algebraic task. So what I want Wolfram to do is solve 0 equals 1 minus y. Again, find the equilibria. You're always just setting the derivatives equal to 0 and seeing what you get. 0 equals x to the second minus y to the second. So just give it those two equations and see what it says. It says x equals plus minus 1, y equals 1. Right, so there are 2 points. X equals 1, y equals 1. X equals negative 1, y equals 1. And that's all it says. Anyway, so that's how I got that. I just asked Wolfram, and it gave it to me. You should have gotten the negative 1, 1 was an unstable saddle, whereas 1, 1 was a stable spiral. So let me just, again, show you the picture here. Put this down. And you can, of course, look at these in GeoGebra if you want to. Here's a slope field of the global system. So I've got negative 1, 1 there, 1, 1 there. Again, globally, this is certainly not a linear thing. We saw no picture that looked like this in section 9.1. However, you see the spiral there, right? See the saddle sort of thing there, right? So if I zoom in on, let's see, this point. Let's take a mental image of that. Okay, see that saddle sort of behavior there, right? So now if I zoom out and I plot the corresponding locally linear system, turn this off. See? Same thing, right? And again, if you zoom in on this, what do you see? You see that sort of spiral, don't you? You know, a hurricane like that where it's kind of oriented left to right like this, I guess. Now if you zoom out, and again, if I turn this off, I look at what I see at the origin, I see the same spiral. Isn't that nice? So then in the aggregate, right? Whoops, not zoom in. In the aggregate, you have sort of a mixture, right? You have a saddle on the left and a spiral on the right, and they kind of like meet in the middle or something, right? So what's the point of all this? What's the punchline of all this? The point is, if you have some nonlinear dude like this, and you want to know what happens in the system, right? Then what you can do is you can find the equilibria, classify them just like we did, and that allows you to sort of cobble together an idea of what the system looks like, what it's doing, right? It lets you sort of see the slope field without having to plot it on some level, right? You can say things like, and again, I'm sorry, I should say asymptotically stable here. I keep forgetting that adverb. But anyway, since we knew there was an unstable saddle over here, and an asymptotically stable spiral over there, this picture or something like it should come to mind. And we know that like when we're over here, we're going to get sort of sucked down the sink right here. But if we started over here, we get sort of sucked over to this dominant eigenvector and be shot off over here to positive infinity on the vertical axis and negative infinity on the horizontal axis. So having this tool in our toolkit of this main result of section 9.3 will allow us to analyze these ecological models in the next section. So in the next section, we're going to use all this. I should have put this at the end, right? We're going to use all that to answer questions like this. So in this system here, what did we learn? We learned that this was stable, asymptotically stable. It was a node. We learned that this was unstable. If you trace through all the work, you will learn that this is also unstable. You learn that this is also unstable, right? I mean, you guys did trace through all the work, right? So since coexistence is stable, what would we predict? We predict that this and this would both flow to 500. Okay, so you're going to flow towards an equilibrium. There's only one attracting equilibrium in the system, and it's that one. So if I bring this up, let me plot that point. Okay, yeah, so I got to zoom back out. Oops, is this the right one? Yes, this is the right one. Okay. Zoom back in here. Yes, okay, turn that off. Turn this on. Okay. Yes, so if you start with 1200 in X and 900 in Y, that's like 1.2 comma 0.9 in this language, right? So you're up here somewhere. So if you follow the arrows, you're going to sort of go like this sort of path, right? Right to left and then sucked into that point. So species X will die, right? And so they'll recover a little bit and then be sucked into this point. Right? So leftward movement is bad for X. So you move left, you recover, and move right. So that species goes down for a while and then recovers. Species Y just kind of steadily declines until you reach that 500 mark. So in other words, if there are this many of X and Y, the system can't sustain both of them. There must not be enough food resources or something for numbers that high, which is why you would stabilize at 500, 500. There's sort of like implied carrying capacities in a system like this. So anyway, that's where we're headed, and that's how we'll finish out the semester, by answering questions like that.